We're starting this morning on learning outcome 3, so in the second half of the year up until June time will be learning outcomes 3 and 4. Okay, so starting today we're going to have a look at trigonometry, sine waves, and some of this will be revision from what we've already done before in science and a little bit earlier in this module, and some of it will be new, some of it you might have come across in school mathematics or physics or something. Okay, so angle measurement in degrees and radians we're going to look at. Pythagoras Theorem, which should be real quick and easy because I'm pretty sure you all know about that. Solving right angle triangles, which is basic trigonometry. Looking at the sine and cosine rules so that you're able to solve non-right angle triangles. You can solve any triangle. The area of any triangle. We're going to have a look at the graphs and of sine and cosine functions, and revise what we did in science on sine wave in the form of a sine omega t plus or minus phase angle alpha. Alright, so it's seen quite a lot, but a lot of it we've already covered before anyway. So let's press on. When we talk about angles, we can either measure them in radians or in degrees. Okay, we always talk about positive angles in clockwise. Around a circle. Yep. So if we talk positive angles go round that way, negative angles anti-clockwise. Yeah. So if we look at the circle in degrees, 0 is always the left to right horizontal. Okay. At the top we have 90, 180, 270. This could also be called, and quite often is, certainly in electrical use of angles and phases and things, negative 90 degrees. Okay, and this could be plus or minus 180 depending on which way you travel. Okay, and then in radians, well, yeah, you could do, but you wouldn't normally do that. You'd go with 90. But yes, if you're going that way round the circle, that could be minus 270. Yes, yes, it could. All right. So, radians is around the constant we all know and love, pi. Okay, and there's 2 pi radians in a complete circle. So 90 degrees is equivalent to pi over 2 radians. 180 degrees is pi radians. 3 pi over 2 is the 270. Okay, and the complete circle, so that's 0. And it's also 2 pi. So we started at 0, that's gone all the way around the circle. We've done 2 pi radians. Radian angles are important for the form of the sine wave that we use. All the 2 pi, omega is always 2 pi times the frequency. Okay, it's also important in the learning outcome for mathematics, calculus. You can only do calculus on angles in radians, not in degrees. Okay, so we have to use radians, and we do need to be aware of making sure we're in either degrees or radians correct as to what we want the answer to come out as. Otherwise you get a completely wrong answer and you calculate. Alright? So, how about converting between the two? We've covered this before. How about it? If we've got an angle in degrees, how do we convert it to radians? (69 125 degrees). We want to convert it to radians. How do we do that? We haven't got Google. Turned it off. How else? Come on. How can I work out what 1 degree is worth? The whole circle, the pi radians. So half a circle is pi radians. So if we divide that by 180 degrees, we've got what 1 degree is worth. Yeah? And then if we multiply that by 125, we've got 125 degrees is worth. If you do that math on your calculator, you should get 2.182 radians. (69 degrees 47). That little symbol there is minutes. There are 60 minutes in a whole degree. Yeah. So we can write that as 69 47 sixtieths. Is that angle? All get that? Yeah. To write tiny little angles also have seconds. There's 60 seconds in a minute. So like time. We multiply that by pi over 180. And we get, and you should get, 1.218 radians. You can leave the rad off. If you don't put the degree symbol, radians are assumed. Yeah, so when you do angles in degrees, make sure you always put the degrees and minutes symbols. Otherwise, radians is assumed. Everybody get that? How that works? Yes. So then, conversely, on the next page, how do we convert degrees, radians to degrees, and indeed minutes? A 0.749 radians. How do we get it in degrees? The whole circle is worth how many radians? Or half a circle. Most people do it with half a circle. So how much is half a circle worth? pi, yeah, multiply it by 749. I haven't got the answers written down on these ones, so hang on. No, there's something wrong there somewhere. Pi over 180. That's right. 180 over pi. Said it was the other way up, then put it the same way up. Right, now do it. How much? 42.91. How do we turn the 0.91 into minutes? Because that's what the question's asking for. We've got 0.91 of a whole degree. Yeah. And there's 60 minutes, because that's the fraction of a degree. Whole degree is 60 minutes. So we got 42 degrees and 91 hundredths of a degree. 0.91. So you do 0.91 times 60, you get 54.6. So let's say 55. So it equals 42 degrees, 55 minutes. Rounded to the minute. Yeah. B, we're doing 3 pi over 4 radians times 180 over pi. Yeah. What could I immediately do there, boys? I could cancel pi out, which often happens in these problems. So 3/4 of 180, 135. Right. And that, if you have a go, or if we have a look at these ones, no, because that work out exact, doesn't it? Just, you do it on your calculator if you like, but 1/4 of 180 is 45, and 3/45 is 135. So it's no minutes. Right? If you look at these problems, you'll see that often more useful not to evaluate pi, as the following demonstrates. So here we want 150 degrees in radians. That's that. Yeah. And if you do that on your calculator, if you've got it set up right, you should get the answer like this. We've got it set up to give you answers in simplified form that won't evaluate pi. And if you're going to carry that calculation on into another calc, you're better off with it as 5/6 pi radians than you are making it a decimal and then rounding it, because you're introducing an error that you didn't have to. Oh, what? Like this, 5/6 pi, same thing. Yeah, because you could say that you can put that pi up on the top line there. That's effectively 5/6 times pi over 1. If you multiply that out, you get that. So you can write that conveniently like that or like that, and that's the same thing. Yeah. However, be careful, because if you had something like that, that is not the same as 5/6 pi. Yeah. So be careful. All right. So you'd find you also find if you do 270 degrees times pi over 180, you should get 3 pi over 2 radians, and we had that on our circle in the first place. That's the 90 degrees downwards. So minus 90 degrees is also equal to minus. Sorry, there's the same angle as that. Yeah. And another one, 37.5 degrees. So you would do times pi over 180. That comes out to 5 pi over 24. And like I said, particularly if you're using them in follow-on calculations, don't evaluate pi. You may have to evaluate it at the end with your final answer, but in the intermediate calculations, if you can, leave it at pi. All right, everybody happy with that? Right, again, Pythagoras Theorem. That is, in any right angle triangle, square on the hypotenuse is equal to the sum of squares on the other two sides. I think you all should be pretty familiar with this from school. If we want to find the length of the side EF, that's this side D here, how would we do that? We'd say we know that the length of DF squared is equal to DE squared plus EF squared. I hate that when they label triangles up like that. But never mind, we'll go with it now. And then, so what we need to do, that's the square root of that as well, isn't it? So how do we go about rearranging that so that we can find EF? How do we get rid of the square root sign? square both sides. So df squared is equal to de squared plus ef squared. Subtract the de squared, so let's have our ef squared over here, because that's what we want to find, is equal to df squared minus de squared, and then lastly we want ef, not ef squared, so square root both sides. Df is equal to root df squared minus de squared. Yeah. And in this case, that is square root of 13 squared minus should be 12 centimeters. I don't think I need to labour on Pythagoras theorem too much, do I? All happy with that? Right angle triangles, length of sides. You come across it in engineering for mechanical, doing forces that are not perpendicular to a direction, and in electrical theory as well. Right. AC electrical theory. So you're going to use through your studies, you'll use Pythagoras theorem quite a lot. All right, so you're all happy with that. Trigonometry for right angle triangles. Again, revision. So if we take a right angle triangle, side lengths A, B and C, and an angle theta, sine, cosines and tangents are ratios related to the sides. So the sine of an angle is equal to the opposite side divided by the hypotenuse. Cosine is the adjacent side divided by the hypotenuse, so that would be A over C. And the tangent is the opposite side divided by the adjacent side. Now sometimes it's useful to use the inverse trig ratios. So they are secant, which is the inverse of sine. So instead of being opposite over hypotenuse, this is Sophocles. Please look the wrong way. That looked like the inverse cosine. That's the inverse sine, and that's the inverse tangent. We won't use them a great deal, to be honest. I'll put them in there for completeness. I will check that, because something don't look right about that to me. I haven't got my book with me, so I'll check it when I go back, and we'll sort out that's good. Right. But the inverse, so there's an inverse to the sine, there's an inverse to the cosine, an inverse to the tangent. So we can use those ratios to solve right angle triangles. So in the right angle triangle PQR, find the lengths PQ and PR. The normal way to label a triangle up is to put capital letters on the angles, so there's PQ and R, and the small equivalent letter on the side lengths. So the hypotenuse is Q, that one's R, and the bottom one's P. Yeah. So in triangle PQR, find the lengths PQ and PR. How can we do, what sine ratios can we use to relate P and Q to the angle 38 degrees? Yeah, cosine. You guys have all been taught soccer tour. I was taught, some officers have, curly auburn hair till old age. Haven't forgotten it. Anyway, soccer tour will do fine. So we can use, can we not, the cosine ratio to find this, because we can say cosine of 38 degrees is equal to the side little p divided by hypotenuse q. Yeah, and then we can rearrange. What are we going to do first? We want to find q. Multiply by q, so we can say q cos 38 is equal to the side length p divided by cos 38, so q is equal to the side p over cos 38. Make sure your calculator's in degrees. That's the side length p, 7.5. What we got? Sorry, 9.5. 3 more on that. Is it 7? Yeah, correctly rounded 1/8, I believe. Yeah. Okay. Now, what's the ratio that you would use to calculate R? What ratio would you use to calculate R? Yeah. Okay, you could use Pythagoras. What ratio could you use? You've got, what sides do you know? Do you know that? You know that now, yeah? Because you just calculate it. So you could use cosine on the calculated, yeah? So you're going to calculate that value with a calculated value there, and in some cases you might have to. But why not use the known value here? We've got the opposite side and the adjacent side. What ratio? Tangent. Yeah. So we can say tan 38 is equal to the adjacent side, the opposite side, which is what we want to find, is it not? R. R over P. Are you happy for me to do that all in one go, those two swap places? Yeah. So P is R over tan 38. That's 7.5 over tan 38. And the answer to that is to R, that goes to R is equal to P at 38, which is 7.5. Yep. Now you can do it. I did ask you if you're all happy with that, and you all said yes. And the answer is, please? Yeah. And as Toby rightly said, you could have calculated that using Pythagoras Theorem. But let's check. We got the square root of 7.5 squared is one side that was given in the first place, and the other side is 5.86 squared. What does that equal? Not if you square root it, I didn't. 9.518, which is the answer we got for the hypotenuse the other way. The point I was making here about using the tan rather than the sine is you're only using one calculated value. So here, for the second part, we could have gone, because we'd calculated that one, we could have used sine, opposite and hypotenuse, but we're using the calculated and rounded value, whereas using the tangent, we're still using our given value from the question, unrounded, which is good practice. All right? Right, moving on. Sine and cosine rules. So, if we want to solve triangles that are not right angle triangles, and we don't know the perpendicular height, we have two further rules we can use. So, labeling the triangle with capital A, B and C on the corners, with the side lengths opposite an angle, the lowercase similar letter. So we got side A as opposite angle A, and so on. Doing that, the sine rule is that A of a sine A is equal to B of a sine B is equal to C of a sine C. So we can use that rule only when we know one side and 8 angles initially given, or two sides and an angle but not the included angle. So one side and two angles, we can use the sine rule, and we can use it if we got two sides at an angle but not the included angle. So when we say included angle, if our two sides are A and B, we can't use the sine rule with angle phi. Yeah, we could if we had A or B. Basically, you have to be able to fill any two, or have three values in two of those ratios. So you can use, if you've got A, sine A and B, to find sine B, and so on. Right? The other one is the cosine rule. In terms of side A, we can say A squared is equal to B squared plus C squared minus 2bc cosine of A. So it looks a little bit more complicated and probably is a little bit more tricky to rearrange, but not that tricky. This rule may be used only when we know two sides and the included angle. So if you've got that issue with the sine rule, two sides and included angle, you can't use it. You can use the cosine rule. Yeah? And because if you look at this, this relies on you knowing two sides, b squared and c squared, and the included angle A. Yep, b squared, c squared, included angle A. You can also use the cosine rule if three sides are initially given. That involves you rearranging the equation so that you've got the cosine of the angle on the opposite side, on the left hand side of the equal sign. Alright? So, let's see, that's that. We'll have a look at a problem in a minute, I would think. And then the area of any triangle, three different ways, depends on what you already know. If you know the perpendicular height and the base, so in this case, the base is A. If you know the distance from little a to big capital A, you can do half base times perpendicular height. We've got this formula's half AB sine C, half AC sine B, or half BC sine A. Or you can find this intermediate variable S from A plus B plus C over 2. So if you know all three sides, and then you use that, you put the value for S in that formula, gives you the area. Alright, not going to derive any of them. If you're in need of those, they would probably be provided in some kind of formula sheet if you do an exam. I know you don't do exams, or they're in your notes for you to be able to look back at, or you'll be given them in the task in the assignment. Alright? So, let's get you to have a look at this. In a triangle XYZ, angle X is 51 degrees, angle Y is 67 degrees, and YZ is 15.2 centimeters. Solve the triangle and find its area. And on the following page, there's a second example. Alright, I'm going to give you let's have a look what I have to do. I'll give you 10 minutes to have a go at this, please. Alright?